Today we're going to revisit melting point order from our unit on bonding and intermolecular forces. First, let's remember that there are two types of forces that are at work in matter. Bonds, which are the connections between atoms that occur within molecules. It's what connects atoms together to make compounds. There are actually four types of bonds present in the universe. We specifically looked at covalent molecular, metallic, and ionic bonding. Generally speaking, covalent compounds have weaker bonds than metallic bonds, which are in turn weaker than ionic. If you wanted to identify covalent compounds from metallic compounds and ionic compounds, you can look at a formula. If the formula contains a metal and a nonmetal, or some combination of polyatomic ions, it's an ionic compound. If the compound's formula contains only metals, it's a metallic compound. And if the compound contains only nonmetals, then it is a covalent or molecular compound. When considering melting temperature, the very first thing that you want to do is to consider what kind of bonds are present in the molecules and evaluate what type of bond they have. And once you can ascertain bond type, then you should be able to put them in order of melting based upon the weakest bonds, covalent, will take less energy to melt than metallic or ionic. The other kind of forces at work in matter are intermolecular forces, the forces of attraction that are very weak in comparison to bonds. These are the forces of attraction that hold one molecule to a neighboring molecule in a sample of a compound. For weakly bonded matter like covalent compounds, intermolecular forces are what is used to discern what type of state the matter will exist in at a given temperature, and can also be used to help judge why things melt at a quicker or slower pace based upon intermolecular force. There are three types of intermolecular force. The weakest is London dispersion intermolecular force, followed by the mid-strength dipole-dipole intermolecular force, followed by the very specific but very strong hydrogen bonding intermolecular force. Okay, we use intermolecular forces to compare melting temperatures of covalent compounds, and intermolecular forces can be predicted based upon molecular polarity. Here's an example of a question that some students had trouble with. Notice the question says, given the melting point data in the chart above, give an explanation for why the order of melting temperature follows this chart from lowest to highest. Okay, in the chart we have CH4, CH3Cl, H2O, water, and aluminum oxide. And the melting point order goes from lowest to highest. The very first thing that I want to do is I want to look at the chemical compounds that are given, and I want to decide what kind of bonds are present. If I look at the highest melting temperature chemical, it contains a metal and a nonmetal. I know that that is an ionic compound. Brass is a type of metal. Brass only contains metal atoms, so I know the bond type for brass is metallic. Water is made up of the nonmetal hydrogen and oxygen. CH3Cl are made up of nonmetals carbon, hydrogen, and chlorine. And CH4 is made up of carbon and hydrogen, which are nonmetals. So I know that the three remaining chemicals are all covalently bonded. So based upon bond strength alone, I know that the covalent molecules have lower melting temperatures because they require less energy to disrupt the bond, okay, and allow melting to occur. Metallic have higher bond strengths than covalent, and ionic have even higher still. So broadly, I can determine melting point order by bond strength. But I have a little bit more discernment to do because I have three different compounds on the covalent end, so I need to understand why they melt in the order that they do. Since we identified each compound on the basis of bond type, now we need to establish a reason for the order of melting for the compounds with the same type of bonds. Covalent compound melting point order is often due to a difference in intermolecular force types. The types of intermolecular forces are London dispersion, dipole-dipole, and hydrogen bonding intramolecular force. Since covalent compound melting point order is often due to the difference in intermolecular force type, we have to investigate what is taking place. What is it that's causing the difference? Molecular polarity allows us to discern which type of intermolecular force is present in a sample. Looking at the Lewis structures of a molecule allows us to decide on polarity and in turn allows the deduction of the type of intermolecular force prominently present. So how does a Lewis structure indicate polarity? Take a second and think about that. Okay, when a Lewis structure is drawn, you can evaluate the Lewis structure if the Lewis structure has lone pairs on the central atom, or if there are different kinds of side atoms on the central atom, then the molecule will display polarity. It can have either or both of those features. Now, once you identify polarity, okay, how does that account for the type of bond type or intermolecular force type, rather? Okay, London dispersion is a type of intermolecular force that is present amongst all molecules of any type, but they are only present and important for nonpolar molecules. They're present in everything, but only important amongst nonpolar molecules. Dipole-dipole and hydrogen bonding are both associated primarily with polar molecules. Dipole-dipole intermolecular force strength is stronger than London dispersion forces. It is important to note, though, if you have a polar molecule will have London dispersion forces associated with it, as well as the stronger dipole-dipole forces. So it has twofold the amount of force. In molecules that are polar, displaying hydrogen bonding intermolecular force, they have London, dipole-dipole, and hydrogen bonding intermolecular force. But it must be noted that hydrogen bonding is a very specific type of intermolecular force that's present only in polar molecules and only amongst polar molecules that contain hydrogen, and that hydrogen is specifically bonded to either a fluorine, oxygen, or nitrogen atom, okay, which are highly electronegative. So now that we have learned a little bit more about the intermolecular forces and evaluating Lewis structures, here are the Lewis structures for the individual covalent compounds that are listed in our chart. CH4, as you can see, has no lone pairs drawn on its central atom, and the side atoms are all of the same type. So I can tell you this is a nonpolar molecule. CH3Cl doesn't have lone pairs on the central atom, but it does have a different side atom. The difference in side atom will cause a polarity to exist in this molecule, and that makes it polar. Water is a molecule that has lone pairs on the central atom, and those lone pairs cause a distortion in the electron cloud, making this molecule polar. Now that we know that each molecule's polarity, we can now predict the predominant intermolecular force type. Nonpolar molecules are associated primarily with London dispersion force. The middle molecule, CH3Cl, is polar. It contains hydrogen, but the hydrogens are not connected by a bond to either fluorine, oxygen, or nitrogen. So this molecule is simply predominantly going to have dipole-dipole force. But remember, if a molecule displays dipole-dipole force, by default, it also has London force. So it has two kinds of intermolecular force. Now, the third molecule, water, has hydrogen, and that hydrogen is bound to the highly electronegative atom oxygen, which means the predominant intermolecular force in the water molecule is hydrogen bonding intermolecular force. But since this is the predominant intermolecular force, you do need to know that water molecules display both London and dipole and hydrogen bonding intermolecular force. So there's threefold force associated between the molecules of water, which makes sense given the specifically higher melting temperature that water has compared to the other two covalent molecules. Now that we've learned all this information and gleaned it from our chart, okay, we can answer the question. The melting point order is arranged lowest to highest because the compounds with weaker bond strength require less energy to melt. In general, covalent bonds, displayed by these three compounds, are weaker than metallic bonds, which are also weaker than ionic bonds. So the order is primarily established due to bond type. For all compounds having covalent bonds, the melting point difference is first of all due to the bond type, but can be further discerned due to the intermolecular force type and the difference in molecular polarity. Okay, and remember, the intermolecular forces are the forces holding each molecule to a neighboring molecule in the sample. Specifically, in this instance, nonpolar CH4 has only the weakest London forces. CH3Cl is polar, having both London and stronger dipole-dipole forces. And water has the strongest intermolecular forces, displaying London, dipole, and the strongest hydrogen bonding intermolecular force as its most predominant intermolecular force. Okay, so these sets of evidence give the best explanation for the question at hand. There are some instances where you might have a pair of molecules that are arranged in a melting point order scheme that have the same bond type and exactly the same intermolecular force type. It's then and only then that you can use the evidence size or molecular complexity. That should be the last choice when deciding melting point order. It's always bonds first, then intermolecular force type. Hopefully, this clarifies your understanding of melting point as a function of bond and intermolecular force strength.